Thank you all for taking time and attending this webinar. We have great content for you all. This is a tool that NREL developed over the last year, and we are excited to present this tool with you all. In this webinar, we will be demonstrating an open source toolkit that NREL developed for distribution utilities. This toolkit will be helpful for DISCOMs to assess impacts of emerging technologies and convert challenges to opportunities. Speaking of logistics, this webinar is being recorded. If you have audio issues, please contact help desk, and the number is on slide here. We love to have your questions answered. Please use the questions pane to ask questions, and the moderator will bring the questions up when it's right time, and we will try to answer as many questions as possible. Here is how we will utilize the time we have. In the first part of the webinar, we will provide necessary background and context about EMeRGE that will be demonstrated later in this webinar. In the first part of the webinar, you will hear more of context and background of EMeRGE, the need for EMeRGE. And after the first part, we will have questions and answers. After the presentation for the first part, we will get into the demonstration of EMeRGE, which will be followed with another round of questions and answers. Hence, there'll be 2 rounds of questions and answers. There's plenty time for that. Ask as many questions as you think that comes to your mind. We will be demonstrating EMeRGE toolkit in this webinar. EMeRGE is an open source toolkit that NREL developed, and the abbreviation stands for Emerging Technologies Management and Risk Evaluation on Distribution Grids Evolution. EMeRGE helps utilities convert challenges posed by high penetration of distribution system located solar to opportunities for DISCOMs. EMeRGE can help further accelerate distribution system located solar approval process to within a week or even lesser. DISCOMs can totally avoid elongated wait times and be streamlined in the process. The demonstration at the end of this, towards the end of this webinar, will have you all learn how to take advantage of this open source toolkit for streamlining your day-to-day processes regarding solar interconnection, understanding their impacts, approval, and so on. Let's move on to identifying who all worked on EMeRGE. I want to thank the team. Without the team, we could not have done this at all. We have an amazing team behind EMeRGE. Kudos to all of them. In today's webinar, you will hear from Killian McKenna as well as Kapil Dwadi as we move on with our slides. Even before we get into what EMeRGE is, I want to set the background and the backdrop. Let's start with today's power distribution grid. As you all are aware at this point, in one way or another, today's power distribution grid is a host for diverse emerging technologies such as solar, battery storage, and electric vehicles. These technologies, if not properly handled, can quickly turn into a series of complex challenges. EMeRGE tool was built to address these challenges from lessons learned from personal interactions with DISCOMs in India, coupled with lessons learned as NREL, as being a national lab, worked with Hawaii and California and translate the challenges that discoms are in front of or facing to opportunities without surprise costs or be as streamlined as possible. Let's get into the contextual situation of India here for a minute. As you all are aware of the renewable energy targets in India, I would like to highlight that 40 gigawatt of the target is earmarked to happen out of rooftop solar, or you can also refer to them as distribution system located solar. This level of penetration at distribution levels can pose serious challenges to grid, can as well, if not properly handled, break the grid in locations, and subsequently forcing discoms to think about expensive system upgrades where you might have to think about distribution transformer upgrades, miles and miles of line upgrades, and so on. How can we convert challenges to opportunities, right? These are all real questions. These complex challenges can be converted. That's exactly why EMeRGE is in place. We took 1 year to build this with all our experience already existing. Because we have implemented lessons from interactions with discoms in India, as well as from Hawaii and California, we can confidently say that the tools that are part of this EMeRGE toolkit will certainly be helpful for furthering the adoption of solar with minimal to no complications. EMeRGE can help discoms accelerate the adoption by leveraging advanced inverters that come with solar. I will be speaking a little bit about advanced inverters in the coming slides. So let's move on. EMeRGE, the way we have built it is it's meant to be for everyday use in discoms. It's not something you use when you see a problem in any way. You use it for every day. That's how we have built it. It has specific modules that can help you all in numerous ways. EMeRGE allows engineers to make informed decisions and design interconnection guidelines promising reliability, economic competitiveness, and sustainability. All of these in the end promise a very stable network infrastructure, which is reliable, having low cost TR integration possible, and in the end, having a easy way to perform load management with the intermittent resource that comes with solar. EMeRGE can help utilities assess risk with oncoming solar and with or without advanced inverters. In the demonstration, you will see a deeper dive into how these risks are even assessed and what do they even mean. Let's take a minute to familiarize with advanced inverters because you will be hearing about this all through the webinar. I'm confident you will be aware of this just to set the ground flat here. I understand everybody is aware of this. Legacy PV systems are those that existed since the beginning, where sole responsibility of an inverter is to convert power generated from solar panels to a consumable form, which is the AC power. Over the last 3 years, these inverters have advanced to a state where they can provide grid services by correcting system voltage and frequency. But I want to caveat by saying that EMeRGE as a tool is meant to only model voltage correction and not anything about frequency. What else can advanced inverters do? Advanced inverters can inject reactive power with some intelligence to it. That's why they're also referred to as smart inverters. Either the advanced inverters can inject reactive power as a ratio of active power being generated, which is referred to as fixed power factor, or advanced inverters can identify how much reactive power to inject into the power grid based on the voltage at the point of interconnection. And that's what volt var is. Also, if there is excessive voltage, advanced inverters can also curtail or reduce its generation, active power generation, to further help the voltage management. In the end, advanced inverters is, in a nutshell, extremely helpful for discoms. That's what is currently being used in Hawaii and California. And we hope that all of these knowledge helps discoms in India as well. Moving forward, my colleague Killian will take over, and he will provide a specific information about interactions with Indian utilities and discoms at this point. Thank you.
Great, thank you, Adarsh. In this section, we are going to cover an overview of EMeRGE and talk about some of NREL's work with discoms in India. So NREL has been providing technical assistance to discoms, particularly in Tamil Nadu, and we have created EMeRGE for utilities across India to evaluate distributed energy resources. So EMeRGE is a tool to help you evaluate solar applications today, tomorrow, and into the future. So your problem, or the major challenge that you'll be assessing tomorrow, is how do I evaluate new interconnection applications? So with ambitious renewable energy targets across India, PV applications are set to surge, which means that there's going to be an increasing amount of solar applications that utilities will have to assess day to day. That's going to create an increased burden on discoms to try to evaluate, can my network accommodate these PV systems? So if you look at the top right here, this is one of the capabilities that EMeRGE comes with, is to help you evaluate new interconnection applications and help utilities and discoms make decisions on whether to accept or reject interconnection application requests based on their technical challenges. EMeRGE can also help with network planning. So this part is, okay, what is going to happen in 4 years' time or 5 years' time? How do we plan for a system with thousands of PV systems on the network? So EMeRGE can help identify which assets, such as transformers and lines, which will be most impacted by high penetration of these distributed energy resources, these solar systems. Also looking to the future, EMeRGE can also help discoms evaluate advanced inverter functions. So NREL has investigated these customized volt var or volt watt, essentially these advanced inverter functions that provide voltage supports for India discoms. And we can help identify those advanced inverter functions to help solar integration in India. So again, this is EMeRGE looking at tomorrow, which is interconnection application. Into the future, how do we plan for a network with a lot of PV systems? And then how do we plan for grid support as well from advanced inverters? Next slide. So EMeRGE is a holistic distribution system analysis tool. So it helps utilities assess their planning and operational needs, and it allows for quick assessment of interconnection applications and these high penetration of future solar systems. EMeRGE uses available data at India discoms. So we've been working with discoms in India, taking their GIS data, building these network models, taking their billing data to try to assess how much energy is used on the network and what time that's used at. Taking weather data to try to look at, okay, how might temperature impact things? How does a radiance impact solar profiles? Taking the SCADA data to look at some of those time series measurement points, and then specific use case data, such as, okay, I want to assess a scenario where a very high penetration of PV. So we take all of this data that is already there at a lot of Indian discoms, and we create these feeder models and load models to try estimate what is going to happen and model what is going to happen on the network. And we take all of that in order to produce all these different analysis capabilities. So looking at risk at a network level, at an asset level, risks associated with network violations. I'll get into more of those in a second. Looking at loss of life on assets and how that is affected. efficiency and power loss, and then looking at some specific use case metrics as well. Okay, next slide. So what can EMeRGE do and what can it not do as a tool? So EMeRGE analysis capabilities include looking at the load shapes and load profiles, doing some peak load analysis, doing time series power flow, so analyzing at each point in the day, what do the flows look along transformers and lines and how are they impacted? Taking DISCOM GIS data and building these network models that can help you assess power quality. And distribution hosting capacity, so that means how much PV can a network safely accommodate. Transformer, line, and thermal loading, so are assets being overloaded or is asset loading being reduced? How are equipment lifetimes assessed, the transformer life assessment, and helping with these interconnection application assessments, trying to see is there any technical challenges with some of the equipment that customers want to install, and then looking at advanced inverter functions such as volt power and volt watt. So right now, EMeRGE is really focused on solar systems, but we are planning and developing assessment on battery energy storage, electric vehicle assessment, and demand side management. So what is not an EMeRGE? So EMeRGE cannot be used to do harmonic load flow, looking at network dynamics such as outages and voltage ride-through scenarios, network protection schemes, asset sizing, and load forecasting, and propensity or adoption modeling. So when their consumer is going to be adopting solar systems, but EMeRGE can help answer at what levels will EMeRGE need to be used. Okay, next slide. So the way that EMeRGE does this analysis is looking at different distribution networks to help with decision making. So there we're looking at power quality violations. How do assets or new introduction of DER change voltage violations on the network? How long will they last? How many customers might they impact? What's the magnitude of those violations? And the same thing for thermal violations, looking at lines and transformers. How frequently are assets overloaded or not? What's the magnitude? How many customers are impacted? Then looking at losses. What are the overall electrical losses on the network? How are they distributed amongst different lines and transformers? And looking at transformer loss of life. On there, we're considering temperature and loading of the asset under these different scenarios. And then looking at PV over generation. Is there reverse power flow in the network? Is there sufficient solar on the distribution network that power is now going the opposite direction? And looking at specific PV over generation as well. So EMeRGE takes all of these metrics and produces really nice summaries of how are these metrics changing as we have more solar systems on the network. So it helps DISCOMs assess the impact of emerging DER on every network asset to help with decision making. Next slide. So what I was saying there is we take all those decision metrics and we try aggregate them together to see what is the change in risk associated with increasing amounts of DER. And in this case, we're looking at solar. So you look at this graph along the x-axis here is the amount of solar. So as we move out to the right, we're looking at a scenario where there's more and more solar on the network. We are modeling that scenario and seeing what happens. On the y-axis here, we're looking at this aggregated power quality risk. So looking at that risk across transformers and lines and voltages. And what we've seen working with DISCOMs in India is that as you increase the amount of solar systems, your risk actually decreases. So solar systems are providing benefits to the grid. And the reason that is that we're seeing solar systems increase voltages. So taking voltages from a low area to more towards nominal. And we're also seeing that at these kind of mid to high penetration levels of solar systems, that they also reduce the loading on assets because they're providing generation locally. And it's only at very, very high penetration levels of PV that we start to see any risk increase above what utilities are experiencing today. So EMeRGE can help utilities assess that risk across time as you look to more and more solar systems being accommodated on the network. Next slide. So now we're going to open things up for a Q&A to see if there's any questions to this point. And we have around 5 minutes, and Amy is going to help us moderate.
Great. Thank you, Killian and Adarsh, for that really helpful introduction. Yeah, so if anyone has any questions before we get into the demonstration of the tool itself on this overview and the capabilities of EMeRGE, please feel free to put those in the chat and we'll answer as many as we can. First, I just want to get a sense from Killian and Adarsh. This tool can be used in any system, but it was designed working with discoms in India. So can you talk about some of the India-specific model capabilities or India-specific questions that are built into this tool that could be addressed?
Yeah, I can take that one. So one of the great things that we've been using EMeRGE for is to build custom or specific fault var and fault watt functions for Indian utilities for discoms. So if you look at, there's a standard link that Adarsh provided in the previous slide here that references a IEEE standard 1547. And if you dive into that, the standard is really designed for US utilities. So we've taken that standard and say, okay, how might a volt var setting look specifically for India discoms, taking into account that there are different power quality requirements in India, specifically in regard to voltages being a wider band of plus or minus 10% in India. And so that's one of the specific ways that EMeRGE is being customized for India discoms and designed for that.
To add on to that, as I also mentioned, our lessons initially, we learned it from Hawaii and California, right? They were specific to US distribution feeders, and you're all aware that the way feeders are built in USA is way different than European or Indian feeders. So we had to relearn some of the challenges that are specific to three-phase systems in India and help understand how can we translate the lessons from Hawaii and California to Indian discoms. And also our direct interactions with discoms in India really helped us learn specific challenges in utilities in India and tackle those with precision as opposed to bringing what we have from USA directly to India. We took special interest in making sure it's usable in today's grid in discoms in India.
Thanks. And we have a couple more questions. Let's try to get to one, just a clarification. Does EMeRGE look at line transformer loading under N-1 conditions?
Yeah, I can answer that. So EMeRGE is not used for modeling outages or modeling contingencies. It's not a dynamic model. It's a static model. So we're looking at the transformer and line loading under steady state normal conditions. We're not looking at outages. What we do capture though is that when lines and transformers are heavily loaded, that there may be a risk of or an increased risk of an outage in that case. That is something we do capture.
Okay. And then another perhaps clarification question on the voltage level that you're modeling. So is this 33 kV, 11 kV? What's the level of rooftop connection that you're modeling? Or is there a specific voltage?
Yeah, there is not a specific voltage level that we are modeling. I would say that we are modeling from the distribution transformer, which could be 33, it could be 120, all the way down to the customer level. So down to that customer point of connection. So we're modeling quite a wide range of voltages. I would think of, as we're saying, this is for distribution networks. So we're not modeling transmission system, but we are modeling the HT and the LT network and the high tension, low tension networks.
And could this tool be used by users aside from discoms? Are there other potential users for EMeRGE?
Yep, that's certainly the case. In solar installers, universities can use to further the knowledge level standards, committees, or CEA, people who look at how can advanced inverters help power grid at all. Yeah, this caters to not just discoms. It's built to help understand the impacts of emerging technologies on distribution feeders. It's not meant to be only for discoms, meant to be for larger set of people.
And then we have time for one more, and unfortunately this might be the biggest question. But there was a question about best practices to avoid RE curtailment in India. And let's try to limit this to the distribution level. So thinking about rooftop PV.
I think it's a very quick answer I can provide. Advanced inverters and voltage support from reactive power. That's exactly what was learned in USA, especially when Hawaii and California had extreme penetration. The first thing that happens when there is high penetration at distribution level is you can't even approve a new interconnection at all, and that leads to more problems. In order to avoid expensive line upgrades or active power curtailment, which is a big problem, all you have to do is look at reactive power support from advanced inverters, and that naturally brings down all the challenges and makes things so much more easier and usable.
Great. Well, please, if we didn't get to your question, we will try to answer it in the second Q&A. Keep sending in your questions. And now I think it's time to move on to the second part of this webinar, which is the demonstration of the EMeRGE tool. So I'd like to introduce Kapil Duwadi, who will be walking you through the tool.
Thank you, Amy. So hello, everybody. This is Kapil Duwadi. So I'm going to spend next 20 minutes or so to explain and demonstrate the capabilities of the EMeRGE tool. Let's get it started. So the EMeRGE is an open source tool developed in Python and has 4 main capabilities. So to name them out, so first one is feeder model development by integrating the utility data. Second one is ability to define custom PV scenarios and perform analysis on those PV interconnections. The third one is EMeRGE has inbuilt a new set of matrix that allows utilities or discoms to assess the impact of the DERs on the distribution system. And then lastly, EMeRGE also has interactive dashboard that user can launch to visualize analysis results as well as the matrix. I will go in more detail about all these modules in later slide. Before I go into that, let me talk about the requirements for you to run the EMeRGE tool. On the hardware side, you need a laptop or a computer with preferably Windows 10 installed on it. We have not yet tested it with Linux or a Mac system, but we will be doing that soon. And 4 GB of RAM is recommended for the performance. On the software side, Anaconda and Visual Studio Code are recommended software for the environment management and code editing. So these are just our recommendations. You can choose other tools as well. So Anaconda is just an open source distribution tool for Python, and Visual Studio Code is a popular code editing software. However, OpenDSS and QGIS are the required software for the EMeRGE. EMeRGE uses OpenDSS to perform distribution power flow under the hood, and also it uses QGIS to process the GIS data. And all of these tools are open source and free. So let's take a look at the repository. So you can find the code for the EMeRGE at github.com/nrel/emerge. And then it also includes a README file that tells you how to install the tool, and also has sample code for you to start using the toolbox. If you have a GitHub installed in your desktop, you can directly clone and start using it. And on the side note, you can also use pip install command to install the EMeRGE tool. Pip is just a Python package manager for the Python. Okay. So let's go a little bit more detail in the modules of the EMeRGE tool itself. So first, capability is the feeder model development. So EMeRGE has dedicated Python packages to develop the feeder model. So what it can do is that it can take in the GIS data, which is present in the .ssp files, extract all the information about the distribution assets, such as conductors, transformers, customers, and all of that, and convert that into a CSV file format, a more easier to read format, right? Once these informations are converted into a CSV file format, for this, EMeRGE uses QGIS under the hood. The missing informations will be filled out using the default values. The user can also customize those default values and then remove the unnecessary data. So that is called a refinement of the CSV files. Once those CSV files are refined with by filling the missing data and removing the unnecessary data, the next process is convert these CSV files into a DSS files. So DSS file is just a file system OpenDSS uses to perform the power flow, and they are called a distribution feeder model. It contains the information about distribution assets, their technical parameters, and geometry of the conductors, time series load profile, and all of that. So the first step is to convert GIS data into a CSV file format, refine them, and generate the DSS files. One of the important part of the distribution feeder model is a time series load profile. You can input external time series load profile if you have. If you don't have them, EMeRGE also has a capability to take in energy consumption data, high granularity system power and voltage coming from SCADA, weather data, holiday information, and build a statistical load model which will be able to estimate the load profile for different consumer groups, and it will be populated to develop the feeder model. So that's all about the feeder model development that is present in the EMeRGE tool. Once you develop this feeder model, next part is the analysis. For now, only the rooftop PV analysis is included in the EMeRGE tool, but in the future, we will be including energy storage, electric vehicle, and demand response as well. So to assess the individual PV interconnection request, the user can fill out the waveform present in the interactive dashboard. They can input information such as ID, capacity, phase, day of the analysis, and the tool will take all this information and process those requests on the back end, and it spits out the result. You can visualize change in voltage profile, change in transformer loading, change in line loading. So the figure on the right-hand side you're seeing is one of that use case. So it's a voltage map on top of the network because of the installation of a single PV, right? So we'll go in more detail in that in the demonstration part. So this is how you can analyze a single PV interconnection request. If you want to analyze a multiple PV networks in the distribution feeder, then EMeRGE also allows user to define custom PV scenarios. And there are 4 parameters that you can configure in the EMeRGE tool. First one is you can configure how many customers will have the PV. You can specify that by specifying the percentage number of customers with rooftop PV. The second part is you can decide what capacities those PV will be of, right? And to do that, you can define, okay, what is the percentage of the energy the PV is supposed to generate with respect to the total annual energy consumption of a particular customer. So you can define size in that way. Third parameter is where those PVs will be installed. For now, all the customers will be chosen randomly throughout the network, but you can also specify how to choose them by saying, okay, they may be near to the substation, far from substations, or in the middle of the substation, right? And the fourth parameter is you can decide whether those PV systems will have advanced inverter functionality or not. And if you choose the PV to have advanced inverter functionality, you have a flexibility to choose the volt-var settings as well. Let me talk a little bit about volt-var settings. So basically, volt-var settings allows those PV inverters to either absorb or inject reactive power to provide a voltage support at the point of connection, right? So if the feeder is experiencing under voltage, these inverters can inject reactive power to boost the voltage up. And if they are experiencing over voltage, these inverters can absorb reactive power to bring the voltage down. So that's what the purpose of volt-var is. And in the EMeRGE tool, you can specify the voltage threshold when to start injecting or absorbing those reactive powers. So that's all about the settings you can play with in the volt-var. Let me talk a little bit about input and output in the EMeRGE toolbox. So it has a lot of modules, but how the input and output works in the EMeRGE tool. All of the modules present inside the EMeRGE tool follow similar input-output pattern. Let me give you an example of one of the module present inside the EMeRGE, which is responsible for converting the refined CSV files into a DSS files. So basically, for every module, you want to have a project folder, and inside that, you want to put all the input files in an organized subfolders. For example, in this particular modules, you want to have 2 subfolders inside the project folder, one with the name extra CSV, another with a feeder name. So the folder with feeder name contains those refined CSV files as an input, and the extra CSV file contains extra information such as load profile, solar profile, substation voltage profile, and all of that. Once you have defined all those input files inside the project folder using these subfolders, now you can use a configuration JSON file. So this JSON file contains the information such as what is the path to this project folder, what are other settings for the conversion. So all that you can define in that JSON file. The default configuration file will be available in the code itself, and you can modify as your requirement comes in, right? So you can use this configuration JSON file to run those modules, and the conversion process will start. After the conversion process completes, you can see the outputs in the project folder itself. For this particular module, it will export 3 more folders, one with exported DSS files, exported pickle files, and coordinate files. So the DSS file contains the converted DSS files. The pickle files and coordinate files are just extra files that will be used later on to compute the matrix. So this is how the input and output pattern works in EMeRGE. Now I'll go to the demonstration part now. Before that, I'm going to give you an overview of what the test feeder looks like for the demonstration. So the test feeder we have chosen here has about 1,700 customers, 1,000 conductors, and 16 distribution transformers. So the high tension level is about at 11 kV system, and the low voltage level is at 230 volt single phase. And following things have already been done in advance to save time for this demonstration. But remember, all the modules are present inside the EMeRGE tool, and you can do that on your own as well. So what we have done is that we have taken all the GIS data, converted that into a CSV file format, refined those CSVs by filling out missing information and removing unnecessary data. So that's a raw CSV format converted into a standard format. And once that CSV files are refined, then we develop those feeder model, that means generating that .dss files. Once that feeder model is developed, we developed a scenarios for 10 PV systems. So it's basically going from 10% of PV to 100% of the PV in a step of 10%. So we developed scenarios for 10 PV system, 10 types of PV systems. We computed a matrix for all those PV systems from January 1 to January 10 in 15-minute resolutions. And we're going to see the result of that simulation in a dashboard. So let me bring up that dashboard real quick. So this is the dashboard that EMeRGE is capable of deploying. So this has 5 tabs on the top: initial assessment, PV connection request, classical PV, advanced PV, and electric vehicle. We don't have anything for the electric vehicle, but we do have for other 4 tabs. So the classical PV just means that it's a bare bone PV without any advanced inverter functionality. So advanced PV is a PV system with advanced inverter functionality, that is VoltVar that we talked about. Okay, so in the first tab, let's go in more detail here. So in the initial assessment tab, there are 3 parts here. The first part is the load duration curve. This is an annual load duration curve. On the x-axis, it is a percentage. On the y-axis, it's a total load kilowatt. So you can see that we can visualize those load duration curve for 4 different type of consumers, right? We have residential, industrial, commercial, and agriculture. On the top, you can also vary the solar PV penetration. So you can choose the PV penetration. In this case, this PV penetration is based on the peak load of the system. So it is not considering any network under the hood. So you can change this PV penetration. Let me change this to 70%. And what it will do is that it will update those load duration curve. You can see there is some overgeneration here. So this is the first part. Let's go to the second part here. You can also look at a daily load profile. You can choose a day here for that particular year. So if I go, let's say, to 18, and you can visualize the load profile for that particular day. And remember, once you change the solar penetration level, it's going to change all of the graphs here and the tables. So this is the second part. On the third part, you can also look at the important statistics about the load profiles. What is the peak load? What is minimum load? What is the maximum solar generation? When is those peak load and minimum load are occurring? So you can look at the time, value, and those parameters. In the future, if you want to add other parameters, it is also possible to do that. Okay, so this is about initial assessment tab. Let me go to the PV connection request tab. So this is the tab where you can input the information about individual PV interconnection requests, and you can look at the impact of those interconnection requests on the network, right? So here are the parameters that you can play with. Firstly, you can input the kilowatt here. So it's just plotting a point value here. And you can input the name of a particular customer. And to do that, you can go here and you can hover over these networks, and you can see the name of the particular node, and you can input that node on that field. And on the third parameters, we have a phase, whether it's a 3-phase or single phase. If it's a single phase, you can specify whether they are connected to R, Y, or B phase. And you have to input when to begin the simulation in this particular format, and pick a day to start the simulation. Okay, so basically, once you do that, once you have selected all the date and all of these parameters, you can switch this request, and then it will update all the graphs. Just one caveat here. So once you input those requests, what happens is that it will take about 1 minute to complete all the simulations and it spits out the results. So you have to wait about 1 minute here. I've already done that in advance, and then I'll go to that result part. But before that, there are other 2 buttons here. So you can switch these buttons to accept those requests. Once you accept the request, the base file will be updated with this new PV interconnection. And then you can also delete the PV. By selecting this delete PV, you will be removing that PV system from the base file. Okay, so let's go to the result part. So I've already run the simulation for a test case. I'm going to show you that real quick here. So this is the parameters, right? So you can look at, okay, how these NVRI and CRI metrics are changing. And by the way, these are new set of metrics that are incorporated in the EMeRGE tool, and more details will be provided in the report later on. But just remember that these are the metrics for a particular node, for a particular customer node. Now they are not changing that much because the PV capacity we entered is about just 10 kilowatt. And it's a megawatt system, and it's not changing those metrics a lot. But you can look at what is the change in profile here. So this is the first 3 graphs are change in voltage, the voltage profile, line loading heat map, and transformer loading heat map for the base case without any PV system. And then the last 3 figures are the change in the voltage profile, line loading, and transformer loading. You can see that the PV is installed on this big red circle, and it is affecting the voltage on the nearby nodes, but it is not affecting far from that, far from the nodes, right? And you can also look at the impact on the line loading, impact on the transformer, nearby transformers. So all of these you can visualize by inputting that information, right? So, okay, so let's go back here. So that's about a PV connection request. Third tab is a classical PV system. So this system is, again, without any advanced inverter functionality. The first 2 figures are the system level matrix and percentage energy loss. And on the x-axis, you are seeing PV scenarios. So the first is a base case that is without any PV system. The second part you're looking at is a PV scenario. The first scenario, it's a 10%, 100%. So the first 10% means that 10% of the total customers have a PV, and 100% means that the PVs are sized in such a way that they would produce the energy equal to the total annual energy consumption for those customers. So that's what the first and second percentage mean here. And you can look at the impact on the voltage, line loading, transformer loading, and also aggregated effect. So those are represented as a risk matrix. So basically it is saying that what percentage of the total simulation time the customers will be at a risk of being affected by these violations, right? The second parameter is the percentage energy loss. And we can look at a line loss, transformer loss, and the system efficiency. And then the third parameter is we can also look at a percentage loss of life of a transformer. So you can look at for every transformers, this is on the system level, but what is the average loss of life of all the transformers for different PV penetration level. You can also look at overgeneration by PV. And since we are doing only for 10 days, you are not seeing overgenerations here. But once you start doing for a month or a year, you'll start to see overgeneration at a higher penetration level. So those are the 4 high-level metrics that you can visualize. Now, you can also look at those system-level metrics on a time series fashion. So what we did is that we computed all those metrics in a daily basis as well. You can also multi-select the parameters here, and you can also select the scenarios as well. So those are for the time, if you want to visualize a time series system-level matrix. Now, the third parameter here is you can also look at asset-level matrix. So those are system-level metrics. If you want to look at asset-level metrics, you can select which asset-level metric you want to look at. You can select what penetration level you are interested in and at what time period you want to look at. And then it will plot the scatter map on top of the metric for you. So those are the time series asset level metrics. If you want to look at the aggregated asset level metrics, they are represented in this tabular format as well as on top of the network. So you can look at those asset level metrics on the network as well as in the tabular format as well. So you can also look at, okay, you can also make it as an ascending order or descending order if you want. So that's how you can analyze those classical PV requests. The similar format is there for the advanced PV. The only key difference here is that now every PV system will have a volt-var settings. And then you can look at those results here as well. So every result here follows the similar pattern, but remember these results are for the advanced inverter functionality. So that's all we have for the dashboard demonstrations. We don't have anything for the EV for now. Let's go back to the presentation here, and I'll open up for the question here. And by the way, you can install EMeRGE tool using pip command, and the code is in the GitHub repository. Okay.
Great. Thank you for that overview. We have quite a few questions. I think that was a lot of stuff to take in. So first, let me just combine two about the advanced inverters. So can you talk about how NREL designs specific advanced inverter functions for India, and also whether advanced inverters can be used at night, in night mode for voltage control?
That's a great question. We can do that for both night mode as well as for full day. And for the Indian utility, what we saw is that most of the feeders were suffering from under voltage. So when we talk about a volt-var support, it's basically injecting the reactive power from all those PV inverters to boost the voltage up. So yes, so for Indian utilities specifically, we are interested on injecting the reactive power from the inverters, and we can do that control both in nighttime as well as on the daytime. Just one caveat there: if you want to do it for a full day, you might be using a lot more those inverters. So we have not yet done analysis on the life of the inverter itself, but you can do that also. I mean, you can do volt-var for a full day also, but we have not analyzed the impact on inverters in this tool.
Let me add to that. Yeah, NREL, that was a question in California 4 years ago, I guess. I remember personally running simulations on the tools that NREL had 4 years ago on understanding how night mode can help. To answer the question clearly, night mode certainly helps the grid. However, the inverters are, if they are utility owned, then you can do whatever you want. If they are customer owned, then the inverter clips. The natural way inverters are configured is that the moment there is no active power generation, inverter shuts down. You cannot do it unless you take steps to enable it. And there has been a study that NREL did about the life of inverter by using reactive power. There is a public paper and a report on that with my name on it. You can actually find it. And there has been impact on inverter life. I mean, that's one reason why standards do not require inverters to provide support, voltage support at night. But that the whole topic is in flux at this point. Some people think it's good, some people think it's not good. But to simplify the whole question, there is a value you can get by using inverters at night.
Thanks. All right, let's go through some more questions. Does EMeRGE take power quality parameters like harmonics into consideration?
No, so we are not doing dynamic simulation in this case. It's a purely steady state simulation for every time steps. It performs a steady state 3-phase unbalanced power flow.
And then what are the parameters that you need for modeling conductors and distribution transformers?
So most of the information comes from the GIS data, but you can also specify a parameter such as for transformers, you can specify what is the no load loss, full load loss, what are their resistance, reactance, and all of that. For conductors, you can specify what is a wire type, what is the radius diameter of that conductor, and you can also specify length of the conductors. You can specify spacing for the conductors, whether they are in the horizontal spacing, vertical spacing, and all of that for the EMeRGE tool. Yeah.
And then you talked about modeling different rooftop PV connections. Can this be used to assess commercial PV or residential? Can you talk about the range of systems you could model?
Yes, definitely. So basically, for the scenario development, we are considering only the rooftop PVs. But if you want to assess impact of a single PV interconnection that is commercial or residential level, you can input that information on the waveform that I just showed before, right? So you can input for the commercial feeder as well. There is no limit to it. As long as the feeder can handle it, you can see the impact on it. So if you install, let's say, a very big PV system, you will see high loading for the transformers and conductors.
Okay. Some more questions. Can EMeRGE be used to assess distribution network losses?
Yes, it can. So that's what the efficiency metric is all about. So we have incorporated the efficiency metric that is an indirect way of telling you what the losses is in the system, right? So we will be including more features to it by explicitly saying what are the losses every time you step, or what are the aggregated losses of the feeders, but you can definitely do that in the EMeRGE tool.
And can you talk a little bit more about how EMeRGE can help process interconnection requests?
Well, at this point, what I can say is that you can input the phase information, your capacity informations, and where that PV is connected by telling the consumer ID. And we are doing a daily simulation for those PV interconnection requests. So what it will do is that for a selected day, it will look at the impact of those PV interconnection on top of the network, and you can look at the impact on voltage profile, line loading, and transformer loading. And there are a few metrics you can look at to make a preliminary judgment of whether to accept or reject those applications at this point.
Let's see. So NREL's been doing a lot of distribution level work with different utilities in India. Can you comment a little bit about what you've seen so far as some of the challenges to integrating solar in India?
Yeah, sure. So basically, most of the studies that are done inside the NREL is based on the US feeders. What is challenging in terms of incorporating those Indian feeders is that one of the difference we saw is that we have multi-tapping in the Indian feeders. That means from a single transformers, there are like multiple 3-phase tapping coming out. And we also model that in the feeder. And then those customers might be at different phases, and you can, well, essentially in terms of the PV capacity, it will not be a significant difference, but you can input all the informations of the PV system that you can connect on the LT side, and you can input that as a scenarios, and EMeRGE is capable of handling those scenarios and looking at the impact on the distribution feeder.
And let me try to get to 2 more. Can EMeRGE work on hybrid systems like RE and storage, for example?
Well, at this point, we are not including the effect of a storage, but certainly we can include that. But right now we don't have we have not included in the EMeRGE tool the energy storage. We only looked at the impact of rooftop PV and the single PV interconnection request, but we have a plan in future to include those other technologies, right?
And then there was a lot covered today, and the tool has a lot of things that I think people are going to need some time to really investigate. So can you talk a little bit about how people can stay involved or reach out to you if they have questions or get updates if you make any updates to EMeRGE?
Yes, I think the best way is to visit the this link, the github.com/nrel/emerge. And if you want to contribute to the code, you can do that using this Git repository. Also, you can send the pull request in. We'll revise that, and then we'll accept those requests if it seems necessary there. And you can we can also provide an email link where you can contact us as a developers, and we can answer your questions for you.
Okay, great. And then we will, as we mentioned in the beginning, this webinar is recorded, and so we will be sending out the recording as well to all of the participants. Okay, in the final few minutes, unless some more questions come in, did you have another slide, Kapil? Or is that?
Yeah, we can, if we don't have any questions, we can conclude the webinar.
Well, let me add that we will be having another webinar. The date, I believe, is August 4th, but I'll send out an update with the video link for this webinar. The next one will be on another distribution level tool called DGen. And DGen is a tool to help forecast rooftop PV adoption. So we've been using that in India, and it's going to be open source as well. And so that will be our next webinar for those interested in seeing how rooftop PV may be picked up in India. Please tune in for that. Okay, well, I encourage you to check out the GitHub repository. Thank you all for joining. Please feel free to reach out if you have any questions or would like more information about this. I'd sincerely like to thank Adarsh and Killian and Kapil for sharing this tool with everybody and presenting on all its capabilities. It's a really impressive tool that they've developed, and I think it's going to be incredibly useful for utilities, not just in India, but all over. So thank you all very much for joining, and have a great day.